Hello, my name is Jackson Jandreau. I'm a PhD student at the University of Colorado Boulder, and I'm going to be discussing some of the different methods by which to remove noise bias from LiDAR and radar data, and showing how these methods can be applied to analyze gravity wave energy in the stratosphere, mesosphere, and MLT region. In atmospheric data, second-order parameters can be very valuable statistics. Second-order parameters such as variance can be used to derive information about the energy carried by atmospheric waves, which can help us understand global energy circulation and can be used to calculate fluxes, another second-order parameter which is used to determine heat and energy transport values throughout the atmosphere. Both of these values are critical for current studies of the atmosphere, specifically the upper atmosphere, where these types of observations may be key to answer some questions held by the community regarding coupling and energy transport. The issue with these second-order parameters is that it can be difficult to calculate reliable values for them for two reasons. The first of which is that they require good, high-quality data, and that they also require good resolution to accurately represent all the atmospheric processes. The second reason, and the one that this talk is going to focus on, is that these second-order parameters contain an inherent bias due to noise in the measurement process. In LiDAR data specifically, this noise is inherent due to the photon collection process, and thus the variances of fluxes calculated without correcting the bias will be overestimated. To understand this, let's first look at the anatomy of the variance term. Mathematical variance can be found by averaging the squared perturbation of a parameter. We can calculate the perturbation simply by subtracting the background, which can be found by time averaging the signal. This perturbation will then contain two components, a portion representing the deviation from the mean caused by atmospheric waves and real perturbations, and another portion representing deviation from the mean caused by noise in the signal. When this perturbation is squared and averaged together, the two components are expanded, the uncorrelated wave and noise signal should drop, and we are left with a variance comprised of both wave variance and noise variance. However, it should be noted that if not enough samples are averaged together, this cross term may not cancel out, resulting in even more noise in the final variance. When we consider this noise variance bias under low signal-to-noise ratio conditions, the value can become high and even comparable to or exceeding the wave-induced portion. For the rest of this presentation, I will be using temperature-derived potential energy density, or EPM, to demonstrate these effects, as it is a useful parameter which directly scales with variance. In this figure, showing a sample of low SNR data, you can see a clear relation between the bias level and the altitudinally decreasing signal-to-noise ratio. As the altitude increases, the uncorrected EPM shown in black increases steadily, while the wave-derived portion, shown in green, increases at a slower rate, being overtaken by the bias at a relatively low altitude. This hopefully illustrates the importance of the removal methods, which I will describe further soon. The data shown in this presentation is taken from the Iron Boltzmann LiDAR stationed at Arrival Heights near McMurdo Station in Antarctica. The lower region of this data is derived from Rayleigh scattering and is taken at a resolution of 2 hours and 1 kilometer, while the higher region is derived from iron resonance fluorescence at a resolution of 15 minutes and 0.25 kilometers. Here's an example from the MLT region showing both the temperature and the temperature perturbations derived from the data. Three solutions currently exist to this problem, the first of which will be referred to as the noise variance subtraction technique. It attempts to solve the issue of the bias by estimating the value of said bias and subtracting it from the variance. The issue with this method is that when the error is very large, the corrected value can become negative, which is a physical impossibility. The next method is called the spectral proportion method and was presented in Chu et al. 2018. It uses a Monte Carlo simulation to estimate the proportion of variance which is noise-induced and scales down the biased value by this proportion. This prevents negative values from occurring, solving the issue of noise subtraction. The interlead method is the newest of these, presented in Gardner and Chu 2020. This method entirely eliminates the bias by using the covariance of two co-located signals to replace the variance. The issue with this method is that it causes a large decrease in the precision of the observation, which then requires a large sample size to regain that lost precision. The variance subtraction method, as previously mentioned, estimates the value of the noise-induced variance and subtracts it from the biased variance. This traditional method is well presented by Whiteway and Carswell's 1995 paper, which estimates the noise-induced variance using the error in the temperature. The EPM equation is then modified to include this correction, yielding the shown results here. These results clearly show that once the signal's SNR drops enough, the corrected EPM becomes negative and doesn't come back to positive, which again is a physical improbability. The spectral proportion method uses a Monte Carlo approach. It takes the sample of data, generates 1,000 copies of it, and applies random noise onto each, which is scaled by the square root of the error value at each point. Then, for every altitude, a 1D FFT is generated and averaged across all 1,000 samples. The resulting average will then contain peaks sitting atop a noise floor. A ratio of peak to floor energy is calculated, which represents the proportion of the signal which is caused by the wave. This is the value that will be used to scale the EPM. We can see that with increasing altitude, the proportion of wave to noise decreases, which tracks with what we observed earlier. When applied to EPM calculation, we can see that the bias-corrected EPM is definitely lower. However, when we compare it to a forward model, we actually see that this value may still be overestimated. This will be discussed further in a future slide. The interleaved method is a little more complex than the previous two. I will demonstrate a method called altitude interleaving, and later we'll briefly discuss time interleaving. To begin understanding this method, it helps to review how LiDAR data is typically processed. The raw data from the LiDAR system stores photon counts in fine bins, which in our system are 48 meters tall. We can then add the counts of 20 of them together to increase the SNR, resulting in a 1 kilometer wide bin containing 20 of these fine bins. Time binning is also done here, but the details of how that is done will not affect this altitude interleaving. This is done across the entire data set to the desired resolution, and the bin photon counts can then be processed into whichever parameter you want to find. To apply the altitude interleaving method to this data, we can instead sum the fine bins in an alternating fashion, creating two separate samples. Each of these will be time binned the same, so that each coarse bin in samples A and B represent the same altitude and time. If we then do this across the entire observation, we generate two separate samples, each containing half of the photon counts that the coarse bins in the traditional approach did. The whole interleaved approach is analogous to having two independent LiDAR systems probing the same space of atmosphere. In this case, just like in the interleaved method, the two samples will have entirely independent noise, yet their wave measurements ought to be exactly the same. In this case, it should be very clear which portion of the covariance would be entirely correlated and which parts of the covariance would be entirely uncorrelated. Keeping in mind this correlation, we can then proceed to calculate variance from the traditionally derived parameter as we have shown before. Doing this, as before, you end up with a variance due to both waves and noise, which can be seen in the top right here, where if a long enough sample is taken, that cross term ought to cancel out, yet the noise term will remain since the noise is obviously correlated with itself. However, when you calculate the covariance of the two interleaved samples, as we show on the bottom, we see something different. Since the noise in each of these bins should be random mean zero, terms containing this noise cancel out once enough samples are averaged together. If we look at an individual sample processed by the interleaved method, we may still see negative EPM values. This is due to the increased uncertainty caused by only including half of the photon counts in each sample. In the plot on the left, we can see individual observations which are processed by the interleaved method and are shown in dashed green. These profiles show both negative and positive values. Overlaid on top of this is the average of all of these interleaved runs, which we find again to be positive, as the uncertainty has been defeated through the averaging of these samples. We see this in the right plot as well, where the left plot shows around 80 hours of data, and the right plot shows nearly 800 hours of data averaged together. In the left plot, you can see negative values, however in the right, with a larger sample size, these values become positive. This is a good time to mention another downside of this method. If the signal-to-noise ratio is low, it may not be possible to get results from a single observation using the interleaved method, as the results have negative values, as you can see from the plots on the left. Averaging data together can allow the interleaved method to be used just fine, but certain studies may require that small-scale features not be smoothed out through such averaging. In this case, one of the other methods may be a better option. This method was just described in detail for application to typical LiDAR data. When handling radar data, however, where there are many different approaches to generating the measured parameters, you can actually apply this interleaving to the derived radar parameter. For example, if you had an observation of atmospheric winds from a radar, you could take a derived wind data, sum the bins together in an interleaved fashion, creating two samples with uncorrelated noise values. Then, the second order parameter could be found using the techniques shown earlier. Here, I illustrate the time interleaved method, which behaves exactly like the altitude interleaved method previously shown, except that the interleaving of the fine bins is done in the time dimension. Both have the same effect, and whichever one should be used depends on the resolution of the system that it is applied to. Here, all the methods are plotted against each other. The left side of the slide shows plots of the LiDAR data, and the right side shows forward model results. The top row shows high SNR winter data taken during polar night, and the bottom row shows low SNR data taken during polar summer. The left column of each set of plots shows data derived from a small set of samples, around 80 hours. And the right column shows a significantly longer set of data, closer to 800 hours. The details of this model are discussed further in my recently accepted paper, which is soon to be available through Earth and Space Sciences. The variance removal method for both winter and summer, and even in the long set of winter data, eventually becomes unreliable, trending towards negative. Looking at the model, we can see the same trend reflected there. Spectral proportion, however, yields reasonable results in both the large and small samples of winter data and agrees with the interleave method even in the low SNR summer at lower altitudes. However, in the summer at higher altitudes, we can see that it begins to depart from the interleave method. When we compare this with the corresponding plot in the forward model, we see a similar behavior and can see that this is an overestimation from the true EPM in the wave field as shown by the purple line. The interleave method in both summer and winter performs well with a large set of data, but in the smaller data set, even in the high signal-to-noise ratio winter, yields some negative values. This is again reflected by the forward model, where the EPM trends noisily around the modeled EPM, and this trend is tightened up with the inclusion of more samples, yielding a nice reliable result. I've shown you how these methods can be applied. Now I will showcase some preliminary results using them. These methods enable us to derive EPM data over a wide range of altitudes spanning the stratosphere, mesosphere, and the MLT range. They allow us to calculate EPM reliably at higher altitudes than we've previously been able to do. An example of why this is important can be seen on the right. Here I have averaged the winter months shown on the left and plotted the corrected EPM versus the uncorrected EPM. If we wanted to theorize what happens in this gap region between the Rayleigh and the iron data, the story would look significantly different when we look at the uncorrected EPM as opposed to the corrected EPM. This uncorrected EPM over the gap region would show a much slower growth rate than the corrected data does, which would greatly change how we interpret what is happening in this region. Also, the application of bias removal to the Rayleigh region reveals a turning point that isn't quite clear in the biased EPM. These results are, as I said, preliminary, so I don't have answers to these questions yet, but exploring these questions will be my next step. Not only do these methods let us look at the data in altitudes where the signal-to-noise ratio is previously too low, but we can now generate reliable profiles for low signal-to-noise ratio summer months. The plot on the right shows the extent to which these correction methods change the results and even show that the winter EPM with its high signal-to-noise ratio benefit from these corrections significantly. These techniques are critical to studying variances and fluxes in the atmosphere. I've summarized my conclusions from slide 14 here, which gives some guidance on when each of these methods should be applied. I would like to encourage anyone with applicable data who wants to study variances or fluxes to use these methods, and I would be happy to lend assistance if I can. I would also like to encourage you to check out the Earth and Space Sciences paper Dr. Chu and I have published, which is associated with the presentation I just gave, and it should be publicly available before too long. Thank you.